Hi everyone, welcome to Bridging Week in Geology. My name is Ed Anderson and I'm the A-level geology teacher at Queen Elizabeth Sixth Form. What I'd like you to do as part of your Bridging Week activities, engage in two lessons. The first lesson, which follows immediately, is all about igneous rocks and their relationship with magma and volcanoes. Following the lesson, there's a multi-choice quiz I'd like you to do, so good luck with that. The second lesson is about volcanic eruptions and involves a little bit of role play. The volcano is about to erupt. Your job is to try to save as many lives as possible. I hope you enjoy these learning activities, and it switches you on to geology as a possible A-level choice. And if you decide to take geology, I'll see you in September. Igneous rocks are formed by the crystallization of magma. Let's look at some different types. Let's look at these 5 different types of igneous rock which you saw in a little bit more detail. You may have heard of this dark looking rock before. It's called basalt. Basalt is one of the most common rocks on planet Earth. For instance, it forms the top 1 kilometre of the oceanic plates, which collectively cover 2/3 of the surface of the Earth. On a more local level, it also forms some of the world's most spectacular landscapes, such as the Giant's Causeway in Northern Ireland. This next rock is called gabbro. Gabbro is a very hard rock which over millions of years withstands surface erosion and weathering to form upstanding mountains, such as these beautiful mountains in Scotland which are known as the Coolin Hills. Its hardness is also reflected by this amazing photograph of a landscape feature known as Zuma Rock in Nigeria. This entire upstanding monolith is gabbro, clearly very hard, and over millions of years the softer rock around it has been eroded away to leave this feature upstanding. You may recognise this rock. It's called granite. Granite is a very hard rock, and as a result it's often used as an ornamental stone. You may also have some of this at home in your kitchen, because granite is also used as kitchen worktops. Heard of him? He's the climber that free soloed one of the world's hardest rock climbs. And this is what he climbed. This is the spectacular southwest face of El Capitan in California. This huge monolith of granite is about 900 meters tall, so that's about 3 times the size of the Shard in London. You may not have heard of this rock before. It's called dolerite. But you would have seen this rock if you've been here to High Force on the River Tees. The dolerite rock forms the top cap of the waterfall structure, and because it's so hard the River Tees can't erode it and literally just falls over it. And this is the one rock that you might recognise. This is pumice with more holes in it than Swiss cheese. You might have a lump of pumice in your bathroom. It's often used to grind off the hard skin on your feet. The formation of pumice is unusual and unlike many other types of igneous rock, and because many of the bubbles and the holes in pumice contain gas, it becomes very buoyant, and famously pumice is the only rock which can float in water. Now, what sort of observations do geologists make when they study igneous rocks? And in turn, what do these observations actually tell geologists about the origin of igneous rocks? Now, one of these observations I'm hoping that you've made yourself is the very fact that igneous rocks are made of solids, and these solids, such as this one, are called crystals. The crystals which comprise igneous rocks are formed during the cooling of magma, and observations around volcanoes can prove this link between cooling magma and the formation of igneous rock. And indeed, the word igneous actually means fire formed. And as magma continues to cool, more and more crystals form within the magma, and eventually those crystals begin to fuse together to form a crystalline mass, which is known as igneous rock. Now, geologists use the different sizes of crystals in igneous rock for a classification scheme. You can see here that this particular rock, basalt, well, it's made of crystals which are smaller than 0.1 millimeter. So this type of rock is called a fine-grained rock. Dolerite is made of slightly larger crystals. They range in size from 0.1 to 5 millimeters in size, and this is what geologists would call a medium grain rock. And then finally, gabbro, well, that's made of the largest crystals. Now the crystals are bigger than 5 millimeters. Geologists would call this a coarse-grained rock. So why are some igneous rocks fine-grained and others are coarse-grained? Well, what controls the size of crystals in an igneous rock is the speed at which the magma cools. In this animation you're about to watch, the red represents magma, and keep an eye on the timescale at the top. It cools very, very rapidly. As a result, the crystals don't have particularly long to grow and they turn into relatively small, fine-grained crystals. This next animation shows the formation of coarse-grained rock. The coarse-grained rock simply forms because the magma is in a very different location. It's much deeper within the earth, possibly tens of kilometers below the surface. In such an environment, the magma is insulated, and that allows it to cool over a much slower time period, possibly tens, hundreds, even thousands of years. Now that the video is playing, you can begin to see the much slower time scale. The magma loses heat more slowly. The crystals therefore can grow into a larger size, and eventually the crystals begin to fuse together to form a very distinct coarse-grained rock. So simply, the size of crystals in igneous rocks is a function of where the magma was and the speed at which the magma is cooling. So magma at the surface cools pretty quickly, so the crystals can only grow into smaller sizes and the rock ends up being fine-grained. Beneath the surface, underground fractures contain relatively smaller bodies of magma, so these can cool a little bit more slowly and turn into rocks which are medium-grained. And then deep below the ground, the very large magma chambers, which are insulated, well, they cool much more slowly and eventually turn into rocks with larger crystals, known as coarse-grained. One observation I'm hoping that you've made as you've been watching this presentation is very simply that the different types of igneous rock, well, they come in different colors. So you have light-colored igneous rocks, such as granite, darker ones like basalt and gabbro and dolerite. Now, the reason igneous rocks have different colors is because they are comprised of crystals or minerals which have different colors. So for instance, granite is made of mineral crystals which are relatively light colored, pinks, sometimes colorless, and white, whereas darker rocks, well, they are made of mineral crystals which are darker. And the reason why the mineral crystals have different colors is because they have different chemical compositions. So at a simple level, the color of an igneous rock very simply reflects its chemistry. So let's explore the relationship between color and chemistry in a little bit more detail. For instance, the rock granite is an example of what geologists call a silicic rock. Now, the first two letters of that term give you a clue as to its chemistry. Silicic rocks are primarily made of silicate. In turn, silicate is made of two elements, silicon and oxygen. Now, when the rock was still magma, the slow cooling of the magma allowed the silicon and the oxygen to combine with some other elements and form silicate minerals or silicate crystals. What type of silicate minerals? Well, one of the most obvious minerals in granite is the pink mineral, and that is called orthoclase feldspar. And the chemistry of orthoclase feldspar is silicon and oxygen, which makes the silicate. But orthoclase feldspar also contains a large proportion of aluminium, potassium, and sodium. Another type of feldspar which forms in granite as the magma cools is pelagiclase feldspar. It has a very similar chemistry, so it's made of silicon and oxygen, which forms the silicate. There is also aluminium and sodium, but pelagiclase feldspar is different because it contains a large proportion of calcium. Finally, another very obvious mineral in granite, which is a silicate mineral, is quartz. Quartz is just silicon and oxygen. It is pure silicate. Darker igneous rocks such as gabbro and basalt, well, they are known as mafic igneous rocks. And once again, the clue to their chemistry is in the title. The M relates to the fact that mafic igneous rocks contain a high proportion of magnesium, whereas the F highlights that iron is also a common element in these rocks. Now, when the rocks were still magma, the magnesium and the iron combined with other elements such as silicon and oxygen and aluminium to create more silicate minerals, but these silicate minerals are much darker. That's why we also call them mafic. Now, one of the dark mafic minerals also has a slight green tinge to it, and it's known as olivine. Olivine, well, it contains silicon and oxygen, which makes it a silicate mineral, but as I've already highlighted, it contains magnesium and iron, so it's a mafic mineral as well. Another mafic mineral in these rocks is augite. This is a very dark mineral. Again, it's composed of silicon and oxygen, along with aluminium and calcium and magnesium and iron. Now, you'll notice that mafic rocks are dark, but there's clearly one white mineral in this rock, and this white mineral is plagioclase feldspar, which, as we've already seen, is a silicic mineral made of silicon, oxygen, aluminium, sodium and calcium. The chemistry of igneous rocks also reveals where the magma, which crystallized into the igneous rock, actually came from within the earth. Or, put it another way, the chemistry of igneous rocks reveals which part of the earth melted to create the magma. The outer part of the earth is made of a rocky layer known as continental crust, which in turn is made of two other layers, the upper crust, and beneath that is the lower crust, which extends down to a depth of about 50 kilometers. Chemical analysis of the lower continental crust reveals that it is made of exactly the same chemical mixture which is found in silicic magmas and silicic rocks such as granite, proving that the melting of lower continental crust creates silicic magma. Lower continental crust melts in continental collision zones, where two continental plates have collided, forcing one of them up, which in turn creates mountains, and the other plate is forced beneath to deeper levels, where temperatures rise above the melting temperature of lower continental crust, creating silicic magma. The magma which creates mafic igneous rocks such as basalt and gabbro comes from a much deeper layer within the earth known as the mantle. In particular, there is a hot zone of the mantle known as the stenosphere. Chemical analysis of this layer reveals that it is composed primarily of magnesium and iron along with silicate, proving that mafic magmas originate from this area. This magma from the stenosphere is able to rise to the surface through large tectonic cracks known as constructive plate boundaries or ocean ridges, such as this one which runs through the North Atlantic. Rocks such as pumice, which contain abundant holes called vesicles, demonstrates that magma also contains a huge amount of gas. Within a volcano, pressurized magma is trapped inside the chamber. As the magma begins to rise towards the surface, the trapped gases inside expand violently, resulting in explosions called blasts. This spectacular blast was photographed by astronauts on board the International Space Station. And this video shows another spectacular blast during a recent eruption of Anak Krakatau in Indonesia. So I hope you enjoyed this short introduction to igneous rocks, and you've learned how the appearance of different types of igneous rocks tells geologists something about their formation and origin. What I'd like you to do now is have a go at the attached multi-choice quiz, and good luck, and hopefully I'll see you all in September.